Hey guys, Miss Gosling here. In this video, you're going to learn about rotation curves in dark matter. By the end of the video, you'll be able to describe the evidence and candidates for dark matter. So let's go ahead and get started. On this slide, you can see the understandings, applications, and skills IB expects you to have for this topic. As you can see, one of the main foci here is rotation curves, rotational velocity, and the mass of galaxies. So that's going to be kind of the main focus that we talk about for understanding the why of dark matter. The other understanding is dark matter. And so for that, so we're also going to be talking about the what. So what do we think dark matter might be? So let's go ahead and start by talking about what a rotation curve is. So when I say rotation curve, what I mean is the distance between the orbital speed of a star and its distance from the galactic center, right here. So what I'd like to do is start by deriving the rotation curve based off of just kind of standard Newtonian mechanics. We're going to go ahead and start with a star that's kind of near the center of the galaxy, like so. So a star near the center of the galaxy is going to have a rotation curve such that its centripetal force is equal to the gravitational forces it experiences, since gravity is the only thing keeping it moving in a circle. So in this case, mv squared over r is equal to g capital M lowercase m over r squared, where capital M is the mass of the galaxy as a whole. Now I'm going to go ahead and cancel out my little m's, and from here I get v squared over r is equal to I'm going to cancel out, I'm going to back up a step. Since I'm canceling, I'm going to go ahead and cancel out my m's, but I'm also going to cancel out my r and my r squared. So I get v squared is equal to gm over r. Now, for a star at the center of our galaxy, we can model the mass of the galaxy as a spherical cloud with uniform density. So what that means is that mass, so our density is going to equal mass over volume. And we get that our mass then is equal to density times 4/3 pi r cubed, since we are modeling our center of our galaxy as a sphere, and that is the volume of a sphere. From there, we can substitute that equation for mass into our equation for v squared, and we get that v squared is equal to 4/3 times g times pi times rho times r cubed over r. R and r cubed become r squared, and I get that v is equal to r times the square root of 4/3 g times pi times density. That r is being able to be pulled out of the square root because when I square root r squared, I get r. From this, I get that v is directly proportional to r. So for those stars kind of in that galactic center over here, this is what I expect. This is how I expect their rotational velocity to relate to their distance from the center of the galaxy. Now, for a star that is on the outer arms of the Milky Way galaxy, not near that galactic center, what I get is that Fc is still equal to Fg, and v squared is still equal to gm over r. However, I cannot substitute mass with 4/3 rho pi r cubed because we can no longer understand the galaxy as a mass of spherical density, as a sphere of uniform density. Instead, what we are more treating the galaxy as for our stars in the outer reaches is a center of mass at the center of the galaxy that is a distance off from a star. So this is more like imagining an object on a string rotating around a fulcrum at the center of the string. Or perhaps a little bit easier to even understand is it's a little bit more like understanding the way that our Earth rotates around our sun, rather than understanding how gas particles within the sun rotate around one another. So what we get here then is for our stars farther from the center of the galaxy, we get that v is equal to the square root of gm over r. Thus, V is proportional to 1 over the square root of R. So when I talk about plotting a rotation curve based off of Newtonian mechanics, what I mean is I'm going to combine these two equations. So as I am at that center of my Milky Way galaxy, what I expect to see is the red portion of my curve up to a distance r. Something linear as V, as R, little r approaches capital R, which is the size of that kind of central mass in the Milky Way. Then, once I start hitting the outer reaches of the Milky Way, I expect to see the velocity fall off as a 1 over square root of R function. As you can see on this graph, that Newtonian picture of how our galaxy should rotate is not what we observe. Based on the actual mass making up our galaxy, we expect to see this red line here, this kind of increasing rotational speed up to a point, and then as we kind of hit that center of mass, the edge of that center of mass of the galaxy, we start to have our rotational velocity slow down pretty quickly. Instead, what we see is our rotational velocity increases and increases and increases, barely decreases, and then levels off around the edge. So something is wrong with our theoretical model. Let's talk about what all this means. So first, the objects in the farthest reaches of our galaxy are moving faster than we expected. And we know that speed and mass are related to one another. The larger the mass at that center of the galaxy, the faster I expect objects to move. So what this means is there must be more mass than we can see in our galaxy. The observable mass is much smaller than the actual physical mass that is there. So how do we explain this difference? One of the most well-accepted theories for the difference between the actual and theoretical rotation curves for galaxies is something called dark matter, which is matter that we cannot see, but that we know exists because it interacts with visible matter. Now, it interacts with visible matter specifically through the gravitational force and the gravitational force only. Now, in order for dark matter to explain these rotation curves of galaxies that we are seeing, 85% of matter must be dark matter. Okay, so there's a bunch of 85% of the universe is made up of dark matter, but what is dark matter? All I've done is tell you that there's some evidence that this thing exists, but we haven't talked about what it is. And the reason for that is we don't quite know what it is. However, there are two main categories for dark matter. The first category is called MACHOs, or massive compact halo objects. This is ordinary matter that is just cold enough to not radiate. So an example of a MACHO would be a small planet. So something that we can't observe, we can't see because it's too cold and too small, but that exists and is responsible for this weird rotation curve that we are seeing. However, there are limits to how much ordinary cold matter there can be that we can't see. In fact, only 15% of dark matter can be explained by MACHOs. So that brings us to WIMPs, which are the most likely candidate for dark matter as of now. WIMPs stands for weakly interacting massive particles. So I want to go ahead and break this definition into two parts. So first, weakly interacting. Another name for gravity is the weak force. So when we say something is weakly interacting, we just mean the only force it experiences is gravity. Now, this is a little bit confusing because, as you know, one of our fundamental forces is also the weak nuclear force. So it's a little confusing that we have a weak force and a weak nuclear force. However, the reason we use this phrase for gravity is because gravity is by far the weakest of our four fundamental forces. So when we say weakly interacting, what we mean is interact with gravity. And then when we say massive particles, I do not mean big particles. I just mean particles that have mass. So there's a lot of different theories about what these particles could be. One good example is neutrinos, which we have talked about in the past as having no mass and no charge. However, we know that actually they have a very small mass. Unfortunately, their mass is not enough to account for all of the dark matter that isn't composed of machos. And again, this is assuming that machos make up any of what we call dark matter. One way that dark matter, the search for candidates for dark matter was described to me that I thought was really meaningful was I had a professor who described it as searching through a big house and your keys, are somewhere in the house. This is supposed to be a key. I think it looks a little bit more like a music note, but here we are. So we've got this key hidden somewhere in the house, only we don't know where it is. We know that it's there. We know it has to be there because my car keys aren't anywhere else. But we don't know where it could be. And so what we're doing when we do dark matter research is we are going from room to room, searching high and low throughout the room, and then crossing each room off one at a time. However, what this means is that when you ask what dark matter might be, the only answer I can give is, So with that, let's talk takeaways. First, rotation curves for spiral galaxies don't match the theoretical curve given the amount of visible matter in those galaxies. So that means there must be some matter that interacts with gravity, but no other forces. And that matter is known as dark matter, the two main candidates for which we categorize into machos and WIMPs. And that's because physicists have a really funny sense of humor. With that, I hope you've enjoyed learning a little bit about one of the big mysteries in physics that we still have today. I hope that this has maybe inspired at least one of you to consider doing some theoretical physics research. Or at least pay a little attention to what's going on in the physics world. So with that, best of luck and happy searching.